We want to combine our discussion of heat and work into the first law of thermodynamics. So the first law of thermodynamics tells us that energy can neither be created nor destroyed. The delta U of the universe is 0. So delta U is the internal energy. Whenever we see that capital U, that is the energy. Capital E is sometimes used as well, but U is a bit more common. I like it. So the delta U of the universe is 0. Basically, the energy contained within the universe does not change. Energy can be converted and transferred between objects. So basically, this is that system surrounding designation. So the energy of a system can change, and the energy of a surroundings can change. But those need to basically cancel each other out. Okay, the delta U of the system is equal and opposite of the delta U of the surroundings. So if a system gets hot, so if energy flows into the system as heat, that energy has to have come from the surroundings. If a system does work on the surroundings, it's losing that energy. It's because it's going into the surroundings, right? The system is doing work. The surroundings is having work done on it. Okay? And so this tells us that there's this balance, and we need to be able to account for all of the energy that kind of comes and goes. One of the things that also is really important about this designation is this means that we can, if we're interested in kind of understanding something about the system or the surrounding, we can measure whatever we want because they're directly related to each other. It's just the negative of it. So usually measuring a delta U or a delta H or something of the surroundings is easier. So we do that and then relate it into a change of the system, which is a harder measurement generally to do. So when we want to account, generally we're kind of focused in on accounting for the energy of the system. And so the change in the internal energy of a system, so delta U, you'll note we've dropped the cis because generally if you don't see anything specified, that generally implies it's the system. And so the change in the energy of the system has to be equal to the heat plus the work. Those are the ways that chemical reactions can change energy. And so there's always going to be the heat and the work component basically of those, and those have to add together to give you the delta U, the overall change in the energy. So again, this is kind of an accounting type problem where work going in or heat going in would increase the energy. That's why they have positive signs. And anything leaving would have a negative sign because it's going out, taking energy away from the system. So energy in is always positive, energy out is always negative. We do want to be mindful that sometimes it's not explicitly described. It's kind of used some context. Described what the sign needs to be in our calculations. So let's apply it. A gas expands from 1.7 liters to 3.5 liters against a pressure of 2.2 atmospheres. What is the heat associated with this process if the total change in the energy of the system is 200 joules? All right, gas expands from 1.7 to 3.5 liters against a pressure of 2.2 atmospheres. What is the heat associated with this process if the total change in the energy of the system is 200 joules? So I want to know the heat for the process. So heat has a lot of equations associated with it. We can relate to enthalpy, we can relate to temperature change, all those sorts of things. We don't have any information about that. We'd have some information about a volume, gas expanding, and the total energy of the system. So because we have this total change in energy of the system, that's a sign that we need to use the first law of thermodynamics. That's the sign that we need to be using delta U is equal to Q plus what I want is this heat. So the question then becomes, do I have these other variables? Do I have the change in internal energy? Do I have the work? So change in internal energy is a yes, right? I got 200 joules, that can go right in there. Do I have work? No, I'm not given work, but we know that work has an equation, right? We know that work is negative P delta V. So can I calculate work? Yes. I have a pressure of 2.2 atmospheres. I have an initial volume and a final volume. So I can plug those values in to figure out what the work is.
negative 2.2 atmospheres times 3.5 liters minus 1.7 liters. So that would be negative 2.2 atmospheres times 1.8 liters, which is equal to negative 401, negative 4.0 liters. Jumping the gun. Negative 4.0 liters times atmospheres. Oh, forgot the rest of it. All thumbs here. Liters and atmospheres. Don't want to forget those units. They don't cancel out. They're both just there. So we got our work. Bingo, bango, bongo. Plug it in. So delta U is 200 joules. Is equal to Q plus, don't forget the negative, 4.0 liter atmospheres. So if we look at this, when we take this value, this work, and just plug it directly into there, we can see we have an issue. This is an energy unit, this is an energy unit. They are not the same. These are not the same energy units. That means you can't do addition and subtraction. So this is why we don't commonly use liter atmospheres. Instead, we convert the liter atmospheres to joules. Generally, whenever you do a work equation, you must always want to convert your liter atmosphere answer to joules. Liter atmosphere just not useful. So negative 4.0 liter atmospheres times 101. Joules per liter atmosphere, per 1 liter atmosphere. And so I get 404 joules, finally. Negative 404 joules. Finally use the 400 correctly. So negative 404 joules. So that is what we really want to use for our work, because the joules would match those joules. So now I can take it, and I end up with 200 joules is my delta U value, is equal to the Q I'm after, plus negative 404 joules, which tells me that Q is going to be equal to 200 joules plus 404 joules. So I get that Q is 600 joules. So what we can see here is that overall, the delta U is positive, right? 200 joules. But energy is being put into the system. It's going in as heat. So the system is being heated up. Heat is flowing in. You will note a lot of energy is leaving as work, right? This negative 400 implies that that is work being done by the system. This is actually pretty common. You use heat, you say burn some fuel, heat up an engine in order to get it to do work. And the engine also just gets hot in the process. Some of that energy that you put in as heat does become useful work. That's useful energy, motion directed energy. But some of it just kind of stays in, goes towards heating up your system. It's pretty common that, say your engine gets really hot afterwards. The heat, that making the engine hot, is not useful. That's not directional work. Directional motion. It's just getting hot, but it's pretty common that both of these things happen, and they tend to a lot of times go in opposite directions. You put in heat and you lose some energy as work, or you do work on a system and then some of that heat flows out. Right? You're putting energy into the system, and it kind of starts to dissipate some of that energy as heat. But we can use our delta U is equal to Q plus W to relate work and heat for any
Participation 616, question 3. What is the change in the total energy of a system that has 450 joules of work performed on it and gives off 250 joules of heat? This is the fourth question on participation 616, due Tuesday, June 16th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the change in the total energy of a system that has 450 joules of work performed on it and gives off 250 joules of heat? So we can return to our question of, why do we care about thermodynamics? We can effectively apply and use heat. We can make predictions without doing experiments, relying on things like state functions. you know, that's really, really powerful. You know, the idea of getting delta H from reference data is really useful. And what we can do is we can add work to that list. You know, we can think not just about heating things, not just random energy, but, you know, directed motion as work. How much gasoline should I burn to drive the pistons in my car? Someone figured that out. How much should flow in to get the optimal expansion ratio, so that you're getting, you know, the maximum amount of work, full expansion on the piston, everything's working correctly. That is, you know, kind of a meeting of, say, mechanical engineering and chemistry and a lot of those ideas. And, you know, other things like how can we describe properties of reactions? You know, what does change in internal energy tell us? And that's a good question that we'll be getting to as we kind of move forward. We want to be describing, you know, what does it mean to know the delta U for a reaction? What does it mean to know the delta H for a reaction? Delta H for a reaction is kind of a use. We've used it before. What does that really tell us about the chemistry, about the, say, tendency of reactions to happen? We had, our third participation question in this video. Got a couple more videos left. Looking for any more questions on participation 616, due Tuesday, June 16th. See you in the next video.